Good, so I think we can get started again. So Ludovic is back, and I have to publicly apologize to Ludovic for asking him to do this talk. He didn't really want to. So last year we realized people were interested in the differences between time of flight and Orbitrap, and we mostly had experience with time of flight. So this is what we talked about a lot, and people wanted to hear more about Orbitrap, but also the differences between these. And I thought it would be cool to have a talk that sort of went into those details a little bit. And then we realized there wasn't actually that many people around who had done DIA on both mass analyzers, and so Ludovic is one of these people. So I strong-armed him into giving a talk about it. So Ludovic, I'm sorry. Please go ahead.
Yeah, so for people, I've been establishing and working mostly with Q-TOF, triple TOF data. So I'm relatively new to the Orbi field, so DIA field. So I try to share with you some observation we have done in the last couple of months using this data. It comes partially from QE. You will see some data is from QExactive, some data is from our Lumos that we got a few months ago. So this is just to remind you shortly what I would say to me at least the most difference and the reason why I originally thought like trapping instruments or maybe not the best instruments to work on DIA. So this is type of, so again, this is MS1 space, retention time M/Z of a very short zoomed in versions of this MS1 space. You see in red the isolation window that's used in DDA mode. And typically from each of these isolation window, you get a relatively nice and independent MSMS spectra. And in shotgun DTA, you expect that each of these MSMS spectra is a snapshot of a different peptide. In DIA, the story is very different. This is exact same space, retention time M/Z. And here you see the size of the red isolation window is very, very different. And as you can see here, the difference is that by isolating such a large isolation window now, you basically co-fragment multiple species. And this is what we have seen in yesterday and today. And the way we analyze this data is by interrogating specific fragment ions from these pictures, etc. And the context, the main component is that now the MS2 series is a multiplex recording of many peptides. And this came originally to me to wonder that ion traps are really good at DDA because you can actually sit very long and enrich very low abundant ion species. And I always thought that, well, I was always doubting whether actually ion traps would be actually the best instrument for DIA. Because here, as you can imagine, when you send such a large isolation window, you're in a very different regime than here, when here you have very few ions per milliseconds that flows to your mass spectrometer, while here you have a super high ion flux, and that you will eat at some point, and you will see very fast, basically the trapping capacity of these instruments. So the question was, when we got our thermo machines, I was very interested to look into the performance of the Orbi instrumentation for DIA measurements. So I organized the talks and share with you different observation. Actually, I realized this morning that you have already heard quite a bit from Mike's talk about the fragmentation. I will re-mention about the intrascan dynamic range. And here you will see the connection to the talk I gave this morning about this target and decoys, the distributions, and the data noise, and some discussions about the best usage of the machines, and some slides about the method generations if you want to do it in your lab. So the first steps which we did was basically, and this is something that I usually do each time we get a new instrument in our lab, is to assess the fragmentation performance. So for this, I use actually a tool that was developed by a master student that I supervised some years ago. And the tool is basically, it's a Python script, and you can plug in basically different DDA libraries. And then what the system can do, it can actually cross-check the similarity, the reproducibility of the fragmentation for a given library. It can also cross-check the similarity between libraries, etc. And the point is that here you don't only get like a score, which is like a dot product or anything, but it basically computes back the score and compares it to a benchmark that the student also calculated. And for example, if you have, for example, let's say a dot product of 0.8, you don't only say a dot product of 0.8, is it good or is it bad for similarity between fragments? So what we have here is a dot product of 0.8 means actually like 62% variation in the fragmentation intensity, which is a lot of variance. So we convert also the dot product score into a real like percentage of variance for the similarity of the spectra. So this is the type of things that you hope to have, like plus minus 5% for each of these fragments would be acceptable, but if you start to get like something plus minus 30 or 50% for each fragment, then the fragments they start to pass on top of each other, and then you might start to get trouble if you want to transfer fragmentation patterns from one machine to the other machine. Anyway, so when we got the Lumos, so the data here on the left side is Lumos, 6600 triple TOF as a comparison and a Q-Exactive as a comparison. And what we do here is basically we take the same sample, it's a HEC lysate, we inject it in triplicate injection, shotgun triplicate injection from the same sample, exact same method. And what the machine does, it basically compares between the three, so you make a library from each of these triplicate injections, and then you compare basically the spectra pairwise to each other, and then you compute the dot product of those spectra, and you compute the dot product of all the pairs of identifications, and you get something like 250,000 comparisons. And this is basically what I call the reproducibility of the fragmentation. So if you have the same peptide in 3 different triplicates, or similar, or their MS2 spectra. And I must say I was very impressed by the Lumos performance. So you can see here actually the performance is not so much connected to the fragmentation. So this is what Mike called this morning like this fragmentation that you get on the back of the Lumos. It's on the ion trap fragmentation. So this is like excitation-based fragmentation versus beam type fragmentation. And you can actually see whether you do CID or HCD. So I call CID, sorry, I call it on the ion trap, and the HCD is the one that you happen on the HCD cells, the beam type. And whether you do the fragmentation on either instrument, on either part of the instruments, as long as you measure them on the Orbitrap, you get basically less, between 5 and 6% variation of your fragmentation spectra, which is very, very impressive. And I must say, like, this is way better than the Q-Exactive. And here I don't have the picture. It was actually in the first paper from Umut that I showed you before. We showed also the elite data was also much worse. So Thermo did a tremendous work. I don't know what they did, but the fragmentation reproducibility and accuracy has drastically improved from elite to Q-Exactive to Lumos. So now you can speak about something like it. Less than 5% variance between your MSMS spectra is virtually identical pictures that you can compare and that you can match your data with. So this I was very impressed with the data. So this is Orbitrap. So which type of fragmentation doesn't really matter. It's extremely impressive fragmentation reproducibility. And you can use this tool again now to ask other questions. Like, for example, how similar is my machine to a different machine or to a different library? So in this case here, we were very interested to see, for example, if we could use the Lumos data with the Pan-Newman library. So the Pan-Newman library was the one that was generated in George's paper. And this was basically a lot of runs that we did on the triple TOF 5600 data. And we wanted to see whether we could actually use that library from a triple TOF 5600 data in order to mine DIA from an Orbi data. And as you can see here, there is actually quite some variance. So don't use, for example, CID ion trap fragmentation for if you want to use like a triple TOF library, but if you have an HCD fragmentation on the Lumos or on the Q-Exactive, you're actually very compatible. So 30% is something that we estimated in the first paper to estimate like the portability of the transferability of assays between instruments or between different type of data. So 30% fragmentation similarity supports actually extraction and use of these libraries in the data. As you can see here, the two best hits are the ones which we basically use now. It's the HCD on the Orbitrap, and then the 6600 as a comparison is actually not performing super much better. So of course, the 5600, I did not show the picture here, has almost a perfect similarity. But even you see from the 2 generations of the SIX instrument, the fragmentation has changed significantly, that the library is not actually completely portable from one generation to the next generation of instruments. So in general here, I would say like the HCD Orbitrap measurements is supported. It supports basically the Pan-Human library that George published in his paper. So what you can even do, for example, is actually to check if you tune your machine specifically on purpose to actually improve this transferability of libraries. So here, this is a Q-Exactive data, which I basically acquired on different collision energy. So this is 24, 27, 30, 33. And this is, again, always comparing the spectra that you get to the spectra that you have in your library. In this case, the 5600 Pan-Human library. As you can see here, the more fragmentation, the more collision energy you use, the worse your similarity to the library becomes. And actually, if you use a relatively improved collision energy here of 27, this is where you can basically get the best transferability between the fragmentation between the Pan-Human library of a 5600 and a Q-Exactive data in that case, for example. So this is something that I encourage you to do if you have a chance, if you get a new machine. Check the fragmentation reproducibility. You can check the fragmentation reproducibility at different fragmentation energies. You can also check the transferability between the fragmentation between different machines. And this is something that in general helps you to say where your instrument stands. And if you can actually, if you acquired a lot of libraries on one machine, if you can port it also to a different machine. So this is my conclusion for this part. I must say that I'm very impressed by the Lumos reproducibility of the fragmentation. This is the best I've ever seen in any mass spec data yet. And I think at the moment the transferability of the assays is fairly well supported, even between SciX and thermo machines, as long as you use the HCD mode on the Q-Exactive or on the Lumos. So now I'm going to switch to an intrascan dynamic range question, which was also something which I commented against in the original SWATH paper. And I want now to revisit it a little bit, having the data to discuss about it. So what I speak about intrascan dynamic range is actually a question that is very important for any type of machines. Could be on a TOF machines, it will be limited by the detector. On an ion trap machine will be limited by the trapping capacity of the trap. And basically the question is, if you have a high intense peptide, the blue one, the question is, in the same spectra, I'm not even speaking in the same sample, in the exact same MSMS spectra, what is the height, what is the limit of detection of the smallest diluted peptides you can detect on the side of it? So to run these experiments, we actually did it in the original SWATH paper. And what we did, we basically took 2 peptides. One was mono-labeled, one was delabeled. And the idea is that, of course, they have the same sequence, they exactly coelute, and they just differ by the mass. And we place the DIA window to be, of course, that they fall in the same window. That's all the aim of the exercise. So we capture them in the same window. And the question is, when you have the high intense peptide constant, and you do a serial dilution series of the red peptide, what is the limit of detection that you see for this red peptide? So you see here the blue peptide has stable intensity. This is not normalized data, but it's just to show you the raw data. And this is basically the dilution series of the red peptides. And you can see you can basically detect the red peptide from a stoichiometric 1-to-1 ratio to the blue one down to a sub-picomole range here. And the conclusion I had in the SWATH paper was basically that it was more about the concept of the machine and the data extraction acquisition concept, that the targeted data extraction can identify peptides spanning almost 4 logs of dynamic range. And as you can see here, there is actually no sign of saturation. So we could even try eventually to push the numbers, the concentration higher in the higher range here. Here we run out of signals, but in that range here, I think there is still some place where you can actually even play even a little bit more. So just to show you what it really represents in terms of raw data, this is the MSMS spectra of the apex of that peak here, of this experiment. Do you see the ratio 1-to-1? So 1.2 picomole, 1.2 picomole. You see actually the fragments that I'm extracting here. I labeled the blue one and the red ones. You see the peak in peak view. You see the 1:2 ratios here. Of course, all the red peaks drop by factor 2. 1:8 ratio starts to get difficult. 1:4,000 ratios. Of course, here you're buried into the noise, but you can actually still see the monoisotopic peak of the fragments of the red species, etc. And the data gets very, very noisy, but you can still actually quantify, and the data was still linear and quantifiable until that level. So this is the point where, and here, of course, you can appreciate, I hope, that if you do this in DDA, there is no chance you can detect the red peptide compared to the blue peptide. But that was just a proof of concept about data extractions and how much more data you can extract from such a high interest dynamic range from a same MS2 spectra. And this is the comment that I wrote at that time on the SWATH paper, which I want to amend now. So, so my comment at that time was that a wide intrascan dynamic range, it's actually very important for DIA. It's one of the most important criteria to have a good DIA instruments. And I mentioned that it was it's mostly feasible on quadruple on Q-TOF instruments. And it might be very difficult to achieve on trapping instruments. And my idea at that time is that the point is that if you have 1 million ions that you can fill in your ion trap, and if your high intense peptides is 100,000 times higher than the lowest ones, you will fill up most of the ion trap space by the high abundant ions, and you will have very, very little space left for the small ions on the side. So that was my comment at that time. And when we got the LUMOS, then I revisited that question, and I wanted to check whether ion traps are really more intrascan dynamic range limited than Q-TOFs. And this is the same, exact same experiment. So I repipetted, of course, all the peptides, all the mixtures together. So this is the same 2 peptides freshly diluted in a yeast background, exactly like in the SWATH paper. And this is basically the data. So this is the intrascan dynamic experiment, and this is the limit of detection experiment. So this is here the high intense peptide. It's stable across the entire dilution series. Here you don't have the high intense peptides, because here I performed the dilution series just in the yeast background, but without having this high intense species co-selected in the same isolation window. So here there is no high intense peptides to measure. And this is the results of the dilution series of the small peptide that I get diluted. And as you can see here, actually, all the peptides is pretty much detectable all through the entire dilution series. The limit of detection, I would say in that case here, it's actually at 1 picomole, while without the high intense peptide, the limit of detection is actually at the lowest one, around 600 attomoles. And the linearity is actually very well conserved. So this is the linearity that you have without the high intense species for 3 fragments. And this is the limit of detection that you have basically with the high intense species on the site. So there is a little, so you're 1 step higher with the intrascan dynamic range limitation in presence of high abundant peptides. While if you don't have these high abundant peptides, you can actually still detect the peptide linearly until the very, very end. But I would say at this level here, the difference is completely negligible. So this is my conclusion about that part. So this is something I really wanted to revisit and now fairly assess on both machines. I can confirm that the LUMOS is intrascan dynamic range limited, because you see that it reaches a better LOD if you don't have this high abundant species. But I mean, the difference is completely negligible. You basically in the same range, it's probably also like, I don't know, maybe I measured the sample only once, so it was just to check, and it's probably like also like a variance that you have in the measurements. So I would say the machine has a similar intrascan dynamic range performance as the triple TOF data. So the ion trap doesn't seem to adversely affect the intrascan dynamic range performance of a trapping instrument. So that's just to say, like, I think the machine is a pretty impressive instrument if you want to do DIA. So what we did, we then run into first libraries, and this is the type of data that you would get. So the first test we did was basically comparing Orbitrap data versus triple TOF data. So these are open SWATH type of pictures I showed you this morning. So you see here the decoy distributions, the target distributions. And the data here was, the library that we used was a HEC library acquired on the Lumos. So of course here, and because of the super high fragmentation performance of the Lumos, it's actually very impressive that most of the data from the HEC library, most of the peptides were actually identifiable from the Lumos data. Of course here, because you have a little bit of variance between the HEC ORBI library versus the triple TOF fragmentations, I would not expect anything better than this type of identifications. So everything looks fine. Things started to get a little bit more complicated when you look into the pan-human library. So here we use the pan-human library, which originates from a 5600 triple TOF data. So this is the typical target decoy distribution that we see when we use OpenSWATH. That you can see here, as you've seen also from Isa's presentation this morning, the majority of the assays from the pan-human library, which comes from many different cell types, many different experiments, are not detectable in the HEC lysates. So only a part of the assay library is actually detectable. But then the question came, what happens here in OpenSWATH? Because here you actually expect the fragmentation to be different. Plus, you would expect also that most of the assays should not be present in the HEC lysate. But still, it seems that you have mostly like true targets and almost no false targets. And the thing became even more complicated when I run into the exact same files, exact same libraries into SpectraNote. And in SpectraNote here, especially if you focus on this picture, it looks actually very, very different. So you see here, SpectraNote recovers false targets like in the triple TOF data, very similar, but the data looks very different than in OpenSWATH. And so when I started to see that, I went back to the raw data, and this is a couple of pictures I want to share with you today. So this is the skyline pictures from this data, from Lumos and from 6600. And you see the MSMS spectra on the apex here from both. Of course, the samples were run in different chromatographic systems, so the background and the chimeric co-fragmenting pictures on the back end might be different. But it's just to show you the difference here. You see the difference in fragmentation. But more important is actually when you zoom into here, what's happening is the Lumos data is actually, as you can guess by yourself, it's a lot cleaner than the triple TOF data. And this is something that we knew, and we know that the data of the Lumos is extremely worked out. It's extremely, so it's a Fourier transform data, it's extremely transformed, it's extremely thresholded, but the difference here was really striking. And if you take a peptide which is even more less abundant, you can actually see, again, even more drastic noise showing up in the triple TOF data compared to the ORBI data. And if you zoom, for example, around a peak here, the Y8 ions, you see really like by eye the difference, what is noise and what is not noise. So you can see immediately here what impact it will have in your data extraction. So if you extract your target, for example, the Y8, you get good Y8 signals for both cases. So this is actually, I don't know which color it is. This is the orange color here. So both nice signals. But then, of course, if you extract the decoys, which correspond to the Y8 in the reverse sequence, the decoys basically gets nothing from the ORBI data because there is no noise. And the decoys here gets quite a fair amount of signals from the triple TOF data. And all this actually then impacts on the pictures I showed you before. The ORBI data doesn't extract any false targets. ORBI data extracts much fewer decoys. And this is just because the data itself contains a lot less noise than the triple TOF data. So the question then, the next, to confirm this effect, I basically took the triple TOF data and I say, so what happens if I threshold this data? So you can just remove the noise. So this is just a simple filtering criteria. You say, okay, I want to have my triple TOF data filtered at absolute intensity of 20. So you kick out all the noise. So what happens if I now search this data that looks pretty much like an ORBI data now, and you basically get back not quite as few false targets as before, but this is from the exact same pan-human library. You completely shift the balance between the true and the false targets. So this was something like, I think it's just an observation I wanted to share with you. So we discussed this extensively internally with George, with Hannes, with Ben, with all the people involved in this type of statistical estimation and how it can hold, etc. We still believe that most of our tools will hold and manage still to get this FDR estimation correctly on these pictures, especially because, as I showed you in the picture before, the decoys and the target are treated the same way. So if you have no noise to extract for the decoys, there is no noise to extract for the false targets. So as long as you treat both species the same way, and as long as you actually don't bias the measurements by one way or the another, I think all the systems, all what you've seen this morning, this holds still true, and you can actually still use most of these calculations for this analysis. So this is my conclusion for this part. I wanted to share with you, and I think everybody who has ever opened an ORBI data can realize that the data is actually extremely worked out. I don't know if it's for good or for bad, but it definitely contains very, very little noise. And this will directly impact on the performance of your scoring of your decoys and false targets. So if you open those pictures, also the one that do the tutorial tomorrow, you will see that the pictures will be very similar for the Q-Exactive as the one I showed you today. And so the only thing that you have to be careful about is that you extract enough decoys in order that your decoys actually captures really these distributions, because if you have so little chance actually to extract good decoys, you basically get models of decoys which is very sparse, and that will maybe not reflect really the level of randomness that you want to check for the FDR estimations. And as I say, in principle, we believe that the statistics that we showed this morning, the Q value and FDR estimation should still hold with this type of data as well. And this is a personal remark, which just for myself, but I know that Thermo has some capability to enable like what they call like full profile acquisitions. So non-thresholded ORBI data that you can actually acquire. So the data file size is like 10 or 20-fold bigger because it contains every single noise of all the transients that you record. But I would be super interested to see actually if the noise that they remove, which might be making sense in DDA, whether we can actually, in DIA mode, retrieve a lot of data that was actually hidden until now in the ORBI files. So this is just a side comment about this. So the last couple of comments I want to make is about really like now starting to compare how the machine perform between ORBI and triple TOFs or ORBI and Q-TOFs instruments. And what is the best way we can actually use the pros and the cons of each machines. So this is a drawing, a schema of the Q-TOF instruments. And this is the calculation that we use when we want to estimate the number of windows and dwell time and cycle times that you want to use on these machines. And here the calculation is very, very simple. It's basically the number of windows multiplied by the accumulation time. So here in the Q-TOF, we basically use a fixed accumulation time per MS2 spectra. So this is basically a parameter that you implement into your methods. And depending on the cycle time that you want to reach, you can decrease the accumulation time, you can decrease the number of windows. So these are the two standard setups that we use when you use like a 3 micrometer chromatographic particles. In the Thermo, I will show you in a second, you will see that the cycle time is slightly lower because we actually use on most of those machines 1.9 micrometers because you want peak sharpers originally for DDA purposes. But for DIA purposes, it might be worth actually to open up a little bit the chromatographic peak width in order to get more time for the sampling of the data points. But still, regardless, the math here is very simple. On the thermotype instruments, things are getting a little bit more complicated. So you also have your quadrupole that isolate your precursors, your isolation window. And here on the back end, it's actually, you have two parts. You have the Orbitrap that performs the scanning. And you have the so what they call HCD cells or ion routing multiples, which performs basically where you actually fill the ions and where you perform the fragmentations before sending the ions to measure on the Orbitraps. So here the things get a little bit more complicated. It's also a number of windows, but here the accumulation time is not a single number. It could be either the scan time or the injection time, depending on what is the slowest one. So the machine here will not have actually, in principle, a fixed cycle time. it will depend if you're actually running out of time in the scan or running out of time in injection. So this actually changes a little bit the story. And depending on which mode or which kind of regime you're actually using the machine, it will change a little bit the behavior of the instrument. So here I showed you two different setups. So this is the setup that we currently use in our lab. And this is, I think, the setup that was described in the most recent paper on the IA. And I think in most of the time, you can see actually more conservative way, for example, like 24 or 30 windows. So on Orbitrap, because the machine is much slower than on the Q-TOFs, you will have to decrease a lot the number of windows compared to what we do on the Q-TOFs. But the question is actually, when playing with this number of windows, where do you actually hit the limits? Is it because of the scan time or because of the injection time? And this is a table which is related to our Lumos instruments. This is just to give you the range of times that you can play with. So this is the resolution that you want to scan for at the Orbi. This is the transient length that you need to scan on the Orbitrap to achieve this resolution. And this is the max fill time, the max injection time that we actually match in order to account for like the few milliseconds that you need to send the ions back between these analyzers. So here you have always like a 10 milliseconds overhead where, so for a certain, like for example, if you scan at 30,000 resolution, you need 64 milliseconds. The Orbitrap is kept busy for 64 milliseconds, and during this time you have 54 milliseconds available for trapping on the back end here. So this is just to show you kind of a roughing ideas. And you see here, in order to be kind of in a similar range, here it's actually slower already than the accumulation time that you have in the MS2. So you need to be about that range in terms of scanning in order to have a cycle time within the range of 2 to 3 seconds as well. So the question came then, actually, what is the best usage of the Orbitrap? And this is a bit similar to what Mike showed you this morning, is actually the fill time behavior of the machine in different regimes. And there, this is, I think, probably where maybe our talk are a little bit different with Mike. So here, what I focused on was I focused on the space where the ions are most abundant. So we know, like, for example, the ions are coming mostly in that region here. And there are very few ions that comes in a very high mass range or at a very late retention time. So what I focus my data analysis is on the mass from 400 to 800. And from the retention time from 20 minutes to 80 minutes. So in that box here, what I calculated here, I calculated the fill times. So, and because I scanned here at 30,000 resolution, the fill time, as I mentioned before, will be at max 54 milliseconds. So this is the fastest fill time that you can have, so like few milliseconds. And this is the longest fill time that you can have, 54 milliseconds. And here I plotted basically the median fill time of these bins of time and masses in order to see what's the ion occupancy, let's say, on the ion traps. And this is a DDA mode. And in the DDA mode, as I explained, you use very small, narrow isolation window. And of course there, you basically capture the peak also at a very early beginning of the elution of the peak. So usually you have very little signals, and they're actually there, the trapping instruments need to sit for quite a long time in order to get this 1 million ions, or whatever your AGC target is, in order to get enough ions to do the fragmentation. And this reflects in this picture. You see in most of this space, and especially in this white square box, you see most of the time you're actually filling up to the max fill time. So you're basically filling up always like 50, 54 milliseconds in most of the cases. Some cases you actually fill up a little bit less, like 15, 20 milliseconds, but you rarely feel actually much less, than 15 milliseconds. You see, and this if you represent in terms of like usage of the machine, so this would be basically the average fill time here would be at something like 50 milliseconds in average in all this region, which basically means that you are using 88% of the capacity of the machine, which means that compared to the possible 54 milliseconds max fill time that you can get. Now in the IA, the picture is very, very different. So this is the exact same run in the IA mode. And as you can see here, the colors change completely. So in this region here, which is the most crowded with the peptides, now here what you have, the vast majority of the scans of the MS2 spectra are actually reach the HEC targets within few milliseconds. So I'm speaking here 1 to 2 milliseconds. The ion flux is so large with such a high, large isolation window that you feel you reach your ion trap capacity within 2 milliseconds. The problem is that once you reach the ion capacity in 2 milliseconds, you still need to wait for the Orbitrap for 54 milliseconds to scan. So during this time, the machine does nothing. It's just waiting and wasting the ion beam of ions during this time. And here, this is basically what you see. So you see basically you use in that space of mass and retention time, using 11% of the power of trapping capacity of your instruments. And again, this is the big difference because here we use large isolation windows and the ion flux is so large that you feel just the ion trap in 1 milliseconds. You basically reach your ion HEC targets. Sorry? 15. We use fixed 15 Daltons. This is this setup here. Yeah, sorry, I did not write. This is 15 Dalton windows, 40 times 15. So might be different in the QE. So this is Lumos data. So Mike, I don't know if this is a little bit similar to the plot that you showed, but I think the difference is that maybe I focus here really on the ion, on the really like most crowded regions of the spectra of the maps. But on the Lumos, which has such a bright source, it's very impressive that in 1 milliseconds, you can actually feel already all the ions that you need to measure a good MSMS spectra. So the question that we raised then, well, if you want to actually use and bring this feeling of the ion traps higher, so the question that we raised is that how low can we actually inject peptides in order to fill up actually the ion traps to the capacity? So what we did, we basically did like a peptide dilution series from 2 micrograms, which is 1 to 2 micrograms. This is what most people inject, at least on a Q-TOF. And then we diluted till 3 nanograms. As you can see here, the same picture as before, these regions, of course, gets redder and sorry, here the scale is reversed, redder and redder, which means that you basically now fill up most of the ions basically to the maximum fill time. So here you reach most of the time use 50 milliseconds of fill times, and this is what you see also in these violin plots. Here you add a few milliseconds to fill up most of the species, and now here with diluting the peptides here, you basically see that the fill time now gets to 20, 30, and then reaches basically the max fill time at 54 milliseconds. So this is the regime where you run out of ions. And you basically now, here, this is the max fill time we set in the instruments. So of course, after 54 milliseconds, we want to abort the fill times in order to measure the next window. So this is the max fill time we allow. And here we run out of signals, out of ions, before reaching the HEC targets. But interesting, for example, to compare these 3 different regimes here of 1 micrograms, 250 micrograms, which is kind of the tipping point, and then like a sub filling of the ion. And in number of identifications in the DIA mode, you see actually also this trend here. And the drop is clearly more significant when you actually run out of ions for filling the ion traps. And interesting is also that actually that the CV of the quantification of the triplicates, for example, these were injected in technical triplicates, they were actually still not very much affected by the fill time. So we could actually still get impressive like number and accuracy of quantification even by filling less than 10 or 20 nanograms. So this is just to show you one example where you can actually leverage and use push the machine to the limit of what it can do in order to get the best possible data from your trapping instruments. Now I have a couple of slides for method generation, just to make some points maybe for people that have either of each machine. So this is a picture from Analyst, triple TOF 56 or 6600, doesn't really matter. So here, when you generate a method in Analyst, you basically have, you first need to create a TOF segment. And once you create one experiment with a TOF, you get basically 2 of these buttons. You can either create DDA experiments or a SWATH DIA experiment. And if you click on this one, you get this kind of wizard window. So I personally don't recommend to use neither the quick, not the quick tab here that shows you some kind of very basic parameters. Go to the manual directly, and here, this is the original setups that most people can use. And this is in the case you want to have fixed windows with a fixed accumulation times. But here, I recommend you directly to select that you can load yourself the SWATH files with the windows that you want. So this SWATH file represents basically like a 2-column tab separated in a text document with a start and end of each window. So this is basically like a typical like 64 variable windows that we use and that we describe in several of our papers. And this is basically a tab delimited table that you can input here. And as soon as you input this, you specify the start scanning of the so this is the MS2 scan start and end of the MS2 spectra, accumulation time. So here, this is where you put 50 milliseconds or 30 milliseconds. And here I also recommend, we tried also more recently, we reevaluate this. We still recommend to use high sensitivity. Even though SciEx sometimes recommend to use high resolution, we systematically get better results with high sensitivity. So after you click this button, you basically get your window and method populated with as many, they call them product ion scans. So these are the windows, and you see the windows here is indicated here. And you can check now in each window what's the accumulation time, what's the TOF, scanning range for the Q2 that you have, for the MS2 that you have selected, etc. And this should, of course, reflect what you entered in your methods. So for SciEx, it's actually pretty straightforward. And I really recommend you to use this window text files because it gives you the flexibility. So this is a discussion where also with the MacCOS lab, whether we should use or not overlapping windows, etc., etc. But this gives you basically the flexibility to do whatever you want. So this is really the recommended method for us. So this is screenshots from Excalibur from the Q-Exactive. So here we actually use the DIA experiment button. So you first generate full MS scan, and then you need to generate as many DIA segments as you need. And the number of DIA segments need to match the number of inclusion windows that you specify in your global list. So once you generate it, for example, in this case here, 40 DIA segments, you click the global list, you get the inclusion list here, and then here you fill up basically, this is also a copy paste that you can do from an Excel document, the masses of the, so this is the center of the window, which is different from the SciEx where you have the left and the right borders. Here you have the center of the window, and the isolation width here, you have to specify it in the main method. Okay, so this is a little bit of a difference, and here we use actually a fixed isolation width, and we have like also like still a 1 Dalton isolation window overlap at the side of at the border of the windows. So this is for the Q-Exactive, and this is for the Lumos. So in the Lumos, the method is very different, as you can see. And so I've heard this also from several thermo people. Maybe Mike can comment on it. So they don't recommend us to use the DIA method generator, but they rather actually recommended to use the targeted MS2. So this is, I think there are some bugs in the Lumos DIA method generators. So this is really the recommendation, official recommendation from Thermo. So you do your MS1 segment here, Orbitrap scans. So here you can actually push the resolutions to the level you want. We usually use 120,000. And for the targeted MS2, you get basically this set of parameters. And at the very end of this list here, you get basically the similar table as you had before. You have the center of the DIA window that you can enter, the charge states. So this will be actually useful in order to calculate the fragmentation energy you will apply to this window. And here is actually, it's cut here, but it's the isolation width of the window. So this is 16 Dalton, for example. So it's a 15 Dalton plus 1 Dalton overlaps between the windows. So these are the type of parameters. If you want to go back, I think I sent a PDF to Ben, so you can have a look. So these are the standard parameters that we use at the moment in our instruments, just to give you a starting point. Yeah, so this still indicates this is a legacy from the first analyst. So it's actually, it's not a random mass, it's actually a mass inside the isolation window that the software still uses kind of to calculate the borders. But here it should not, so if you do really like kind of a PRM type experiments, this would be your mass of the targets. But here in DIA, in SWATH, it's basically, it's not really meaningful for you. What matters is really these borders here. But if you use a very old type of converter, sometimes this mass is still referred to. But in practice now, most of the converters now, they basically pick up directly the window width directly. Okay, maybe you can come to the questions later. I have last conclusions and a couple of comments. So I showed you first that the DIA on the Orbitrap, I mean, now many people are using it anyway, but I wanted still to confirm it for myself. It's very impressive. So we have these 4 logs of dynamic range, which is not, so it's, I think there is still a limitation on the RB, on the trapping, but I think it's negligible compared to the power that the machine has. You have a very, very impressive fragmentation reproducibility. You can actually transfer the data between machines quite well as long as you use HCD mode. So it allows you to use publicly available libraries. But the machine is has such a good fragmentation reproducibility. If you want to leverage the power of these fragmentations, it might be worth to consider reacquiring homemade libraries with the exact same fragmentation that you have on your instruments. And there you would leverage really by far the best you can do the relative intensive fragments for the scoring of the peaks, as we've seen this morning. So it might be worth considering using really homemade libraries. So the DI data on Orbitraps contains very low noise, as I showed you. It affects this true and false target distribution, as I showed you, which will look very, very different from Q-TOF data. So don't be confused when you start to see this data. It's just the fact that the Orbi data intrinsically contains a lot less noise. We believe that the Q-value and FDR estimate still holds very well for this type of data, and that you can still use most of the models that we have published on TOF data as well. And so this is my personal take on the machine. So the DI and trapping instrument is best leveraged, according to my point of view, at low sample load, or actually you should make something during the scanning time. So the Orbitrap is very low at scanning, especially if you go for like resolution 30,000 or higher. You will spend 64 milliseconds or 120 milliseconds just scanning. And during this time, don't waste the ion beams. Do something with it. And I think Mike's group has designed this MSX that you will hear more about on Thursday, I believe. And MSX, I think, is a fantastic way to make use of this scanning time that otherwise is lost. And my personal take on this is basically you can actually it allows you to inject very, very low sample amounts and then to actually fill up really and make use of the fill times during the scanning time that the ions otherwise are completely wasted in the trash. So this is my final slide, Q-TOF versus Orbi. So I think you can use really the best of each machines depending what you want to do. So the Q-TOF is really fast. So now we actually have the method that we're currently running. We use like 13 milliseconds, I think, for each MS2 spectra acquisition. So this is a speed that the Orbitrap so far will not be able to match. And this, you can actually increase the number of windows like crazy. So we typically do 100 or 200 windows. And we still maintain a relatively good cycle times. And in parallel, the Orbitrap is very slow. So as I showed you, if you want to go like 30 or 60,000 resolutions, you will have a super slow scanning instrument. So we'll have to limit somehow the number of windows. So either you need to reduce the mass range of precursors, as Mike said, from 500 to 800 or 900. This still contains most of the informative peptides for protein identification. The number of proteins identification don't shrink so much if you scan that range. And you will have to reduce the number of windows to in the range of like 20 to 40 maybe, depending on your cycle time. But on the back end, you have a trapping capability. And there you can actually use it to leverage really the injection time while the machine is scanning. So this is a slow machine, but you can do a lot of things during this time. And I think this is kind of the best usage that we actually try to play with the both machines. So we use the Q-TOFs for very short gradients. So now we typically do like 13 or 20 minutes gradients, so super fast gradients, and a high number of windows in order to get back the specificity for the acquisitions. And this is for like large sample cohorts, high throughput data analysis. And but you need to shoot a lot of samples. And orbit data, on the other hand, because it's so slow and because you have the trapping capabilities, we actually use it now for very low sample loads where you have very few samples you can measure on the machines, where the signals would basically be very, very low on a Q-TOF type of instruments. So this would be basically the best usage and taking the best advantage of both machines. And yeah, thank you for your attention. If you have questions.
Great. Any questions for Ludovic? Isa?
So I checked the ratio. So I'm not sure I understood the question. So I checked the ratio of false targets versus decoys, for example, to give us some kind of an impression if the data is treated the same way. It is a little bit different. So I'm not exactly sure how to make sense of that. But I think, so we discussed this a lot also like in the last couple of days, because before I showed this data here. But we still think that as long as you treat the targets and the decoys the similar way, and if you don't, so this is different than what I said this morning, don't kick out the bad false targets from the distributions, because then you're biasing the targets versus the decoys. But here, in principle, the bad false targets and the bad decoys, they will be kicked out in a similar way because there is no noise to extract them, right? So. Mm-hmm.
And in your Lumos data, you have a false target fraction of 10%, then probably the number of targets that are underlying the distribution is also 40% low.
Underlying the decoy distributions?
Do you mean the absolute number of true targets in the end?
The absolute number of true targets is similar. Yeah, yeah.
True targets.
True targets. Yes, correct. There is no peak. There is basically no peak to score. So the system is just like not finding any peak for any scoring. So this is kicked out from the raw data, basically.
No, this was a question. So
the
absolute number of...
It's similar. The number of identification is very, very similar between SpectruNote and OpenSWATH and between the different ways we operate the machine. So this is very similar, yeah. It's just the ratio of false targets and decoys that change drastically. I don't know if you have seen this in Skyline. I don't know when you, I mean, you are the DIA OB, if you also seen this type of like low number of false targets versus how do you treat them?
So we do know that I think the pi 0 is very large.
Yeah.
We tend to have lots of issues sometimes, and we definitely have cases where a lot of tools just struggle with that because small differences. If you go from like 98 pi 0% pi 0 to 97%, there could be actually 100% error in that going to fit the left-hand side of the curve. I'm not sure if that's exactly what you're getting at.
No.
Other questions? If not, we'll go to Brendan for introduction to Skyline. Thanks, Ludovic.